Okay, so let's see what we were doing before. We were here, so we wrote down S matrix element and we expressed it as apart from these constants as a product of these factors which vanish when k1, k2 these are on shell, so that k1 square is equal to mp square and this becomes 0. Okay, and same is true for other momenta as well. And then we had a Fourier transform of Green's function, okay, with these arguments. Okay, this is an m plus n point Green's function, and we understand that this S matrix element is going to be non-zero only if the G tilde here contains poles in k square plane. So if you have terms like k square minus k1 square minus mp square, then this pole will get cancelled, and similarly other poles will get cancelled if G tilde has such poles. And in fact it should, because this S matrix element should not be 0, otherwise there is no scattering. Okay, so that's the expectation, and that's what we wish to now figure out. So let's start by looking at the most general structure of this G tilde. I have put momentum labels as q1 to qn. Okay, I'm looking at this for any g1 to gn, q1 to qn, and let me also remind you what G tilde is. Okay, this is just the Fourier transform of the Green's function in the coordinate space. So I transform each coordinate, each xi, okay, and the conjugate variable to that is qi. Okay, so let me begin by taking a specific example. Of Green's function in 5 to the 4 theory, which we are at present considering, but whatever I say will apply to any endpoint Green's function and in any theory. Okay, so I will take specifically 4-point function. Okay, conclusions will be applicable in a general theory. Okay, so let's draw some diagrams which contribute to G tilde 4. Okay. So diagrams that contribute are the following. So that's the lowest order diagram. Then we have this diagram, and then many others. Okay. Then we also have these kind of diagrams. And another diagram is this. Okay, I'm arranging the diagrams in a particular way, but as we have learned before, we have to draw all possible diagrams. Okay, but I'm just doing some arrangement of this. and one more set I want to draw. Okay, and they are infinite diagrams, okay, because you have to consider all terms of order lambda to the n, where n goes to infinity. Okay, so we have this now. If you write the expressions, see, let's look at this first column. If you write the expression, let me first label the momenta. Okay, and the same thing here, it's also q1, and similarly q2 and others. Okay, and same thing here, so q1 enters here. Okay, so when you write down this diagram and for G, the expression of this diagram for G tilde, you will write I over, so you can visit the first part of this course and you will find that this is what we should write, q1 square minus m square plus I epsilon times the remaining part of the diagram. Okay, when you come to the next diagram, it will have the form I over q1 square minus m square plus I epsilon times, that's the propagator here, this propagator. Okay, then you have this bubble, and for bubble you should write down the contribution. So contribution from the bubble, okay, and times, you remember you'll have momentum conservation at each vertex, so the momentum that flows in this propagator is also q1. So you'll have again I over q1 square minus m square plus I epsilon times remaining parts of this diagram. And you see the remaining parts of this diagram are exactly the same as the remaining parts of this diagram. So let me write remaining parts of the diagram. Okay, and remember, when you are looking at the remaining parts of the diagram, for example, let's look at this first diagram. Okay, what's the expression of this? You have propagator for each of these lines, and then you have vertex which is minus I lambda over 4 factorial. Okay, and then you should supply 2 pi to the 4 delta 4 q1 plus q2 plus q3 plus q4. That's the total momentum. That's the delta function which conserves the momentum, and then you also have to multiply with the combinatoric factor. Okay, so this remaining parts of the diagram contain vertex, combinatoric factor times 2 pi to the 4 delta 4 of q1 plus q2 plus q3 plus q4, and the same is true for this also. Okay, let's look at the third one. Third one will also have exactly the same form as above. Instead of contribution from bubble, you will have contribution from this diagram, okay, this part of the diagram, and so similar thing, I don't want to write it again. And then for the last one, you'll have here 3 propagators, one coming from here, second propagator again coming from here, which will also have a momentum q1 flowing into this, and this one will also have a momentum q1 flowing into this, and that's the case because we have momentum conservation at each vertex and these are loops, right? They involve only dummy loop momentum, so there is no other momentum flowing in, so this entire line will have these 3 propagators will have q1 flowing into them. Okay, and you will multiply these 3 propagators and contributions coming from this bubble and this loop diagram, and then times the remaining diagram, which also includes combinatoric factor. Now, if you sum up the first column, okay, you will get you can factor out I over q1 square, you can factor out the remaining parts of the diagram, okay, because all of these, the way I have organized, all these 4 diagrams have identical contribution for the remaining parts of the diagram which I have written here, okay. Now, look at this second column. It has roughly the same, it has the same structure. That's how I have arranged everything. The only difference is that the remaining parts of the diagram here is different compared to the first column, okay. But other than that, what happens on these external legs is identical, okay. So, you can see that the general structure that you are going to get is of the following form. So, this is my G tilde, let's look at okay, this is G tilde q1, q2, q3, q4, okay, 4-point function. So, I denote it like this. Now, this is equal to let's look at the first line, first leg, okay, in which momentum q1 is entering. When I factor out all this, we have contribution from this leg, we have contribution of this kind, of this kind, of this kind and this kind, multiplying the entire diagram, okay. And the same is here, identical. So, if you sum up these 8 diagrams, then you see that you can factor out this I over q1 square minus m square plus epsilon times these 3 factors, okay, and then remaining parts of the diagram will be a series expansion in which the first term will be just minus I lambda times 2 pi to the 4 delta 4 coming momentum conserving delta function coming from here together with the combinatoric factor plus contribution coming from here, which will have these 2 vertices, again a momentum conserving delta function and its corresponding combinatoric factor. So, the structure would be of this form. This is what we can see from the foregoing discussion. Okay, and this contains the remaining parts of the diagram. This is what is remaining parts of the diagram. And of course, you have sum over all the diagrams. Okay, we have to sum over all. I should write sum. Okay, and what is that sum? That sum contains this vertex, then this diagram here, and if I had drawn another one, let's say this one, then it will contain this remaining part of the diagram. So let me draw one more, it will help to understand. Okay, you see here also I can put exactly this. So this is also a possible diagram in G tilde. So that's how I am arranging everything. Okay. And of course, then you realize that there is nothing special about first leg. I can do the same thing on all legs, meaning I can look at also the contributions of this kind. Well, let's start with the lowest order diagram. So you could have a bubble here, you could also have a bubble here, okay, and also this, there is also this diagram, of course, okay, and all possibilities. So you see that if we go through the argument which told us that we should have structure should be of this form where this contains all corrections on a single line, okay. These are all corrections on this Q1 line, okay, here. So all those corrections I am including in this by, and all those corrections are denoted by this blob, okay. So this blob contains all the corrections, and if I repeat the argument, then it's clear that I should be able to write it as this. Okay, where this contains now not the contribution from all the remaining parts of the diagrams, that is true, but this contains these kind of parts. What goes into this, let me call this as G tilde amp, and of course with the same arguments. Okay, amp is a short form of amputated. Okay, and to amputate means to cut off the limbs. So this part is what you get after you have removed all the limbs. Okay, let's see what it means. So G tilde amputated contains contribution coming from this. From this vertex, okay. So first term will be just this vertex, then this, and so forth, okay. So what is, how do we understand this? So you see here, G tilde amp, the way we have arrange everything, it does not contain any line which you cut, which upon cutting will give you an external point removed from the diagram, okay. So here, for example, if you look at this, let's look at this one, there is no line in this which upon cutting can isolate any external point. So let's say I want to isolate this point, okay, let's say this point. Is there any point which I can, any line which I can cut to isolate this? Well, yes, there is one. If you cut here, then this gets isolated, this becomes this times the remaining diagram, but that is not what goes into the amputated diagram, right? What goes into the amputated diagram is this. Now let's look here. Is there any line which you can cut to isolate this point? No, there is none. Okay, that is how it has been arranged. So you see all the diagrams that enter into G tilde amputated have a property that upon cutting any single line, you cannot isolate an external point. Okay. So for this G tilde, these are external lines, and you can say this is an external point. You cannot isolate this external point by cutting any one single line. Okay, that's important. It should be about 1 point, or 1 line. You cannot cut 1 line. Okay, so that's the structure, and this contains all the corrections to the external leg, and similarly here and here and here. Okay, so let me just write down one time again the expression for G tilde. How do I get rid of this? Yes. So G tilde amputated, okay, or in short amputate, amp is equal to a contribution, did I write it already? No, will be like this. That's order lambda term, then this is an order lambda square term, okay. Then of course you have other diagrams which you have seen in the previous course. Okay, I'll not put the labels Q1, Q2, Q3 and Q4. You understand what I am writing because we have drawn these diagrams several times in the previous course. And also let me draw one more here. Okay, and here let me write down the expression for this. This term will have minus I over lambda 4 factorial times 2 pi to the 4 delta 4 and then you have combinatory factor which will be 4 factorial, right? There are 4 factorial ways in which you can get this, plus order lambda square terms. Okay. This contributes to lambda square, this also contributes to lambda square, this contributes to lambda 4 and so on. Okay, let me try to explain why you have a 4 factorial here. See, after all, we are just writing these diagrams, rearranging them in a particular way. So look at this one. This had a 4 factorial multiplying it, right? Because that is the combinatorial factor. And once I have written it as a product of limbs, and where limb is, for example, this limb is giving 1 over q square minus mp square. Similarly, these ones, where should I include the 4 factorial factor? So that I am including in the amputated Green's function. Okay, in the amputated Green's function, G tilde amp, and not in the external lines. Okay, because that will not be convenient. So those factors are in here. Okay, so now let's analyze this in more detail, and we'll write down the precise form of this Green function as product of these external leg corrections and the amputated Green's function. Okay, that's our next task, to have a precise expression for it. But we already understand what it should be like based on this discussion.